Praise for higher order Perl. As a programmer, your bookshelf is probably overflowing with books that did nothing to change the way you program or think about programs. You are going to need a completely different shelf for this book. While discussing caching techniques in Chapter 3, Mark Jason Dominus points out how a large enough increase in power can change the fundamental way you think about a technology. And that's precisely what this entire book does for Perl. It raises and deepens vaults and highest towers of computer science, and transforms the many arcane treasures it finds, recursion, iterators, filters, memorization, partitioning, numerical methods, higher order functions, querying, cut sorting, grammar-based parsing, lazy evaluation, and constrained programming into powerful and practical tools for real-world programming tasks. File system interactions, HTML parsing, database access, web spidering, typesetting, mail processing, home finance, text outlining, and diagram generation. Along the way, it also scatters small but equally invaluable gems, like the elegant explanation of the difference between scope and duration in Chapter 3, or the careful explanation of how best to return error flags in Chapter 4. It even has practical tips for Perl evangelists. Dominus presents even the most complex ideas in simple, comprehensible ways, but never compromises on the precision and attention to detail for which he is so widely and justly admired. His writing is, as always, lucid, eloquent, witty, and compelling. Aptly named, this truly is a Perl book for a higher order, an essential reading for every serious Perl programmer. Damian Conway, co-designer of Perl 6. Preface. A well-known saying in the programming racket is that good Fortran programmer can write Fortran programs in any language. The sad truth, though, is that Fortran programmers write Fortran programs in any language, whether they mean to or not. Similarly, we as Perl programmers have been writing C programs in Perl, whether we meant it to or not. This is a shame, because Perl is a much more expressive language than C. We could be doing a lot better using Perl in ways undreamed of by C programmers, but we are not. How did this happen? Perl was originally designed as a replacement for C on the one hand, and Unix scripting languages like Bourne Shell and AWK on the other. Perl's first major proponents were Unix system administrators, people familiar with C and with Unix scripting languages. They naturally tended to write Perl programs that resembled C and AWK programs. Perl's inventor Larry Wall came from this sysadmin community, as did Randall Schwartz, his co-author on programming Perl. the first and still the most important Perl reference book. Other important early contributors include Tom Christiansen, also a C and Unix expert from way back. Even when Perl programmers didn't come from the Unix system administration community, they were trained by people who did, or by people who were trained by people who did. Around 1993, I started reading books about Lisp, and I discovered something important. Perl is much more like Lisp than it is like C. If you pick up a good book about Lisp, there will be a section that describes Lisp's good features. For example, the book Paradigms of Artificial Intelligence Programming by Peter Norvig includes a section titled What Makes Lisp Different that describes 7 features of Lisp. Perl shares 6 of the features. C shares none of them. These are big important features like first-class functions, dynamic access to the symbol table, and automatic storage management. Lisp programmers have been using these features since 1957. They know a lot about how to use these language features in powerful ways. If Perl programmers can find out the things that Lisp programmers already know, they will learn a lot of things that will make their Perl programming jobs easier. This is easier said than done. Hardly anyone wants to listen to Lisp programmers. Perl folks have a deep suspicion of Lisp, as demonstrated by Larry Wall's famous remark that Lisp has all the visual appeal of oatmeal with fingernail clippings mixed in. Lisp programmers go around making funny noises like cons and cooler, and they talk about things like PC losering problem, whatever that is. They believe that Lisp is better than other programming languages, and they say so, which is irritating. But now it is all okay, because now you do not have to listen to Lisp folks. You can listen to me instead. I will make soothing noises about hashes and stashes and globs, and talk about the familiar and comfortable soft reference and variable suicide problems. Instead of telling you how wonderful Lisp is, I will tell you how wonderful Perl is. And at the end, you will not have to know any Lisp, but you will know a lot more about Perl. Then you can stop writing C programs in Perl. I think that you will find it to be a nice change. Perl is much better as being Perl than it is at being a slow version of C. You will be surprised at what you can get done when you write Perl programs instead of C. Website. All the code examples in this book are available from my website at perl.plover.com. When the notation in the margin is labeled with the tag some example, the code may be downloaded from that address. The website will also carry the complete text and errata listing and other items of interest. Should you wish to send me email about the book, please send your messages to this email address. Acknowledgements. Every acknowledgement section begins with a statement to the effect that without the untiring support and assistance from my editor, Tim Cox, this book would certainly never have been written. Until you write a book, you will never realize how true that is. Words fail me here, saying that the book would not have been written without Tim's untiring support and assistance doesn't begin to do justice to his contributions, his kindness, and his vast patience. Thank you, Tim. This book was a long time in coming, and Tim went through 3 assistants while I was working on it. All these people were helpful and competent, so my thanks to Brenda Madlisevsky, Stacy Pierce, and Richard Camp. Competent may sound faint, but I consider it the highest praise. Many thanks to Troy, Lily, and Simon Crump, the product managers who were not only competent but also fun to work with. Shortly before the book went into production, I started writing tests for the example code. I realized with horror that hardly any of the programs worked properly. There were numerous small errors and some not so small inconsistencies between the code and the output, typos, and so on. Thanks to the heroic 11th hour effort of Robert Spire, I think most of these errors have been caught. Robert was not only unfailingly competent, helpful, and productive, but also unfailingly cheerful too. If any of the example programs in this book work as they should, you can thank Robert. If they don't, you should blame me, not Robert. Robert was also responsible for naming the mod document preparation system that I used to prepare the manuscript. The contributions of my wife, Lori Kim, are too large and pervasive to note individually. It is to her that this book is dedicated. A large number of other people contributed to this book, but many of them were not aware of it at the time. I was fortunate to have a series of excellent teachers, whose patience I must sometimes have tried terribly. Thanks to Mark Foster, Patrick X. Gallagher, John Livingstone, Cal Lobel, who first taught me to program, Harry McLaughlin, David A. G. Mayer, Bruce Piper, Ronnie Rabassa, Michael Temple, and John Tisk. Mark Foster also arrived from nowhere in the nick of time to suggest the title for this book just when I thought all was lost. This book was directly inspired by 2 earlier books. ML for the Working Programmer by Lawrence Paulson and Structure and Interpretation of Computer Programs by Harold Abelson and Gerald J. Sussman. Other important influences were Introduction to Functional Programming by Richard Byrd and Philip Wadler, and Paradigms of Artificial Intelligence Programming by Peter Norvig. The official technical reviews had a less rewarding job than they might have on other projects. This book took a long time to write, And although I wanted to have long conversations with the reviewers about every little thing, I was afraid that if I did that, I would never ever finish. So I rarely corresponded with the reviewers, and they probably thought that I was just filing their suggestions in the shredder. But I wasn't. I ported over all their comments with the utmost care and agonized over most of them. My thanks to reviewers Sean Burkle, Damian Conway, Kevin Lenzo, Peter Norvik, Dan Schmidt, Craig Sitaker, Michelle Scott, and Adam Turnoff. While I was writing, I ran a mailing list for people who were interested in the book and sent advance chapters to the mailing list. This was tremendously helpful, and I recommend the practice to anyone else. The 650 wonderful members of my mailing list are too numerous to list here. All were helpful and supportive. And the book is much better for their input. A few stand out as having contributed a particularly large amount of concrete material. My apologies to the many helpful contributors whom I have deliberately omitted from this list in the interests of space, and even more so to the several especially helpful contributors whom I have accidentally omitted. Wolfgang Klaun and Per Westerlund were particularly assiduous in helping me correct errors for the second printing. Before I started writing, I received valuable advice about choosing a publisher from Philip Greenspan, Brian Keringan, and Adam Turoff. Damian Conway and Abigail gave me helpful advice and criticism about my proposal. Sean Burke recorded my Ivory Tower talk, cut CDs and sent them to me, and also supplied RTF related consulting at the last minute. He also sent me a periodic mail to remind me how wonderful my book was, which often arrived at times when I wasn't so sure. Several specific ideas in chapter 4 were suggested by other people. Meng Wong suggested the clever and apt odometer metaphor. Randall Schwartz helped me with the append function. Eric Rode suggested the multiple list iterator. When I needed to read out of print books by Paul Graham, A.E. Sunstorm lent them to me. When I needed a copy of Volume 2, The Art of Computer Programming, Hildo Biersma and Morgan Stanley bought it for me. When I needed money, B.B. King lent me some. Thanks to all of you. The constraints system drumming program of Chapter 9 was a big project, and I was stuck on it for a long time. Without the timely assistance of Wim Lehler, I might still be stuck. Tom Christiansen, John Orvand, and Nat Torkington played essential and irreplaceable roles in integrating me into Perl community. Finally, the list of things without which this book could not have been written cannot be complete without thanking Larry Wall for writing Perl and for founding the Perl community, without which this book could not have been written. Recursion and callbacks. The first advanced technique we'll see is recursion. Recursion is a method of solving a problem by reducing it to a simpler problem of the same type. Unlike most of the techniques in this book, recursion is already well known and widely understood. But it will underline several of the later techniques, and so we need to have a good understanding of its fine points. Decimal to binary conversion. Until the release of Perl 5.6, there was no good way to generate a binary numeral in Perl. Starting in 5.6, you can use printf function, but before that the question of how to do this was frequently asked. Any whole number has the form of 2k plus b, where k is some smaller whole number and b is either 0 or 1. b is the final bit of the binary expansion. It's easy to see whether this final bit is 0 or 1. Just look at to see whether the input number is even or odd. The rest of the number is 2k, whose binary expansion is the same as that of k, but shifted left one place. For example, consider the number 37 is 2 times 18 plus 1. Here k is 18 and b is 1. So the binary expansion of 37 1 0 0 1 0 1 is the same as that of 18. 1 0 0 1 0, but with an extra 1 on the end. How did I compute the expansion of 37? It is an odd number, so the final bit must be 1. The rest of the expansion will be the same as the expansion of 18. How can I compute the expansion of 18? 18 is even, so its final bit is 0, and the rest of the expansion is the same as the expansion of 9. What is the binary expansion for 9? 9 is odd, so its final bit is 1, and the rest of its binary expansion is the same as the binary expansion of 4. We can continue in this way until finally we ask about the binary expansion of 1, which of course is 1. The procedure will work for any number. To compute the binary expansion of a number n, we proceed as follows. First, if n is 1, its binary expansion is 1, and we may ignore the rest of the procedure. Similarly, if n is 0, the expansion is simply 0 otherwise. Second, compute k and b so that n is equal to 2k plus b, and b is equal to 0 or 1. To do this, simply divide n by 2. K is the quotient and b is the remainder. 0 if n was even and 1 if n was odd. 3. Compute the binary expansion of k using the same method. Call the result e. 4. The binary expansion of n is eb. Let's build a function called binary that calculates expansion. Here is the preamble and step 1. Here is the step 2. For the third step, we need to compute the binary expansion of k. How can we do that? It's easy because we have a handy function for computing binary expansions called binary, or we will once we finished writing it. We'll call binary with k as its argument. Now the final step is string concatenation. This works, for example, if you invoke binary 37. You get the string 100101. This essential technique here was to reduce the problem to simpler case. We were supposed to find the binary expansion of a number n. We discovered that this binary expansion was concatenation of the binary expansion of a smaller number k and a single bit of b. Then to solve the simpler case of the same problem, we used the function binary in its own definition. When we invoked binary with some number as an argument, it needs to compute binary for a different small argument, which in turn computes binary for an even smaller argument. Eventually the argument becomes 1, and binary computes the trivial binary representation of 1 directly. This final step, called the base case of the recursion, is important. If we don't consider it, our function might never terminate. If in the definition of binary we had omitted the line with return, then binary would have computed forever and would never have produced an answer for any argument.